Okay, so we're going to talk about electromagnetic radiation today. And when I say radiation, it generally has a pretty bad connotation with it. Think about people, getting irradiated like in Chernobyl or various other nuclear disasters. But radiation is not always dangerous. Okay? Not always dangerous. Sometimes very much so, but not always. So what this is energy sent in wave form. And I know this is more conducive to a physics class or a chemistry class. Everybody believes they have the right to be the authority on electromagnetic radiation. And the only reason I'm talking about it in this class is because there's a very little tiny sliver of it that our eyes can detect. And I want to distinguish that from the rest of it. Plus, I feel like it's a great opportunity. Like, I would be remiss if I didn't teach you something about electromagnetic radiation before you graduate high school, because it permeates just about everything that there is out there. All right. Foremost, I want to mention that there is a spectrum, which is really just a fancy word for range, to distinguish between types of electromagnetic radiation. Okay. The difference between types of waves has only to do with their wavelength. That's it. The difference between radio waves and microwaves and gamma waves and ultraviolet and visible light and infrared and all those different types is just their wavelength. That's it. And this is the distance between wave peaks. That's all there is to it. So this radiation travels in sort of a sine wave, okay? And where this would be the direction of travel. So the wave is headed that way. And a wavelength, very simply, is the distance between the peaks of the wave. The distance between the peaks. That's all it is. Now, the consequence of the distance between the peaks and what it represents is quite substantial. But in a nutshell, that's all it is. The difference between radio waves and microwaves is that the wavelength's longer. Infrared is different than microwaves because their wavelength is shorter. That's it. It's all the same type of radiation. It's just that the waves are sometimes substantially shorter. So I'm going to use one of the lines that I already have here because it seems the most intelligent way to have a chance at making a straight line. And this is going to be long on this side. So long wavelength. And on this side, short wavelength. And I can't emphasize how long is and how short is enough. So if we go to the far end of this side, then the long ones can be 100 kilometers or more for a radio wave. Like the distance between the peaks can be like from where we are to close to Festus. Like it's pretty, some of them are pretty long. Most of them aren't quite that long, but that's how long this goes here. So the longest waves that fit into that are radio waves. Radio waves. And radio waves, your examples of those would be like, well, radio. I know that's dumb, but that's the truth. Like if you're tuning in a radio station in your car, you are dialing it in based on how long those waves are. If you're dialing into 96.5, those waves are a little bit longer than if you're dialing into 102.9. Those waves are a little bit shorter. But that's the purpose of the tuner in your car, is to capture waves of different lengths. Okay? Also, your cell phone signal or data is transferred to and from your phone via radio waves to the tower. So it's radio waves that are transmitting these data signals back and forth. That's how that form of communication happens. Also, Wi-Fi. Wi-Fi is your Chromie is sending information to and from that access point in above your heads here using radio waves, sending data back and forth. Okay? Now, if the waves get a little bit shorter than that, then they are microwaves. Microwaves. Some cell phone signal actually gets pretty close to where the microwave frequencies are, and that would work too at sending the stuff. But radio waves, the next one is microwaves, just like in a microwave oven. So it generates a wave that has enough energy to actually heat up organic material, like, you know, burritos and such. Okay? So now, is it to say that all microwaves are dangerous? No. The reason that microwaves like can heat up food and really wreak havoc on aluminum foil is not so much the distance between these peaks, but how tall the waves are sending that energy. In a microwave, there's a lot of energy being sent. Also, if you notice in your microwave where the clear glass is, there is like a mesh in that. Do you remember seeing like there's always a mesh in there? That's because that mesh is the right size that the waves actually can't pass through it, because the waves are too long to actually fit through those little holes. Microwaves are anywhere between a millimeter and a meter in length. So that's where those are. Now your next step on here is infrared. Now I'm going to this is not to scale, but I want you to picture these are long, and then they're getting shorter, and then shorter, and then shorter, and shorter, and shorter. And by the time you get to the end over here, you can't even tell that they're a wave, because the waves are so close together that it's hard to distinguish. Infrared would be two things. Heat. If you feel heat, like from a bonfire, etc., or wood stove, like if you're at a bonfire and that thing's roaring and you walk behind somebody else, you don't feel that heat anymore. But then you step out from behind them, you can feel that heat radiating. That's radiant heat. It's infrared waves that are sending that heat. And also remote controls. For the most part, your Apple TV remote uses radio waves, but like your regular TV remote, very likely uses infrared to communicate. If it's got a bulb like this at the end of it, it's sending infrared waves. And if I point this at your eyes here, you can't see that bulb light up because our eyes can't detect infrared. This camera, however, for some reason converts infrared into visible light. So if I press the button there, it actually lights up. I sometimes do that to test the batteries to see if they're still good. So those are the first three types. Now I want you to put this tiny, tiny little sliver in here. That is all, like these guys all have a pretty good range, okay? But what we're about to do right here, not a very big range. This is known as visible light. Why is the range so small, Mr. Helly? It's because this range is defined by what humans can actually see, and it's a very, very, very narrow band of this thing. Now, in chemistry or physics, you learned what was the acronym for the colors of light you can see? Somebody said it. Roy G. Biv. Roy G. Biv. For red, orange, yellow, green, blue, indigo, violet. Okay. This is what we can see. If it's not here, we can't see it. Now we can see combinations of those things. If you look above your head and you see my LED lights, right now they're white. The reason they're white is in each of those little bulb areas there are 3 diodes. There's a red, a green, and a blue. If I turn just the red one on, then, and I can't do them all at once, then only the red diode lights up. And that is a long wave, okay? If I turn the blue one on, then only the blue diode lights up, and that's a lot shorter wave. If I do the green one, the green diode lights up, and it is somewhere in between those two. But it's a really small unit. It's measured in nanometers. It's very, very small. Now, what happens? Now, I've got all 3 of them on now, and our eyes detect that as white. It's kind of a blue-white, but when all of the diodes are lit up, it's activating all of the color cones in our eyes, and it looks like we're seeing white. Now, what happens if the wave is longer than red? Well, it's no longer visible light. It is what? Infrared, which is why it's called infrared. Infra means less than red. It's not quite red. Okay? What happens if the waves are closer together than violet?
Ultraviolet.
Then you have ultraviolet. Now, when we get over here, it starts to get dangerous. Okay? Because these can deliver a tremendous amount of energy. I think ultraviolet light, shoot, I'm trying to remember. These are about, you can fit probably a molecule in between the waves of ultraviolet light. They're very, very close together. So this would be the sun UV, that's what UV stands for, is ultraviolet, or tanning beds. That's why they work. What they're trying to do is they're putting ultraviolet light on your skin to damage your skin. Okay? That's the goal of any tanning of any kind, is you're causing damage to your skin, which is why it gets a burn. The burn, the reason your skin turns red is because you're sending a lot of blood flow to the surface of your skin to try to repair the damage that the ultraviolet has caused. Your body then responds by activating the melanocytes to produce more melanin and fill in that skin to try to protect it a little bit more from the sun so you don't burn as easily the next time. Now, as we get shorter, we're getting even shorter, we have X-rays. X-rays, you can barely fit an atom in between the rays, in between the peaks, because these are so close together. Now, X-rays, I don't have to tell you what they are used for, because, I mean, it's for an X-ray. You get an X-ray, and the X-ray radiation passes through your skin, and it basically passes through the skin and muscle, gets absorbed by the bone, and as such, that lights up on the X-ray because of the density. But if you've ever noticed, when you have an X-ray done someplace, whoever's doing it sets it all up, they go away because they don't want to be in the room where the X-ray is happening, because it's a lot of radiation. But for you just having a few of them done, one at the dentist's office once a year, or if you break your ankle, it's not that bad. But if your job is an X-ray tech and you subject yourself constantly day after day to X-rays, your likelihood of getting cancer goes up substantially, because this can actually damage your DNA. That's how powerful these rays are. But they are not the most powerful. The most powerful is gamma. And I know that that's supposedly what turned the Hulk into the Hulk. Really, it would either turn the Hulk into a dead person or a cancer patient.
Yeah, I just watched that movie.
Yeah,
it said he should have died.
Yeah, there's this stuff is super powerful. This is what is emitted when there is a nuclear disaster, like at Chernobyl. Chernobyl, like, still nobody can live there or anywhere near there or will ever be able to. They allow some people to visit, like, the perimeter of that town as like a weird, like, tour type thing, but you cannot get close to the Chernobyl, like, nuclear power plant, because it's still emitting so much nuclear radiation that it would damage you seriously to be anywhere near it. They built some kind of a dome over it to try to contain it. But to give you an idea of the scale of damage and how long it lasts for a nuclear disaster, that site is emitting gamma radiation in dangerous, deadly levels, and will do so for the next 4 billion years. It will never stop. Yeah. So nuclear energy is something that has a tremendous potential for energy, but if it's done poorly, has the potential to ruin people and the environment in ways I can't begin to explain. These waves are so close together, you can barely fit the nucleus of an atom in between the waves, which you're like, well, but atoms here, yeah, it's not that different. No, it's a lot different. Most of atoms are space. Between the proton and neutron and the electrons of an atom to scale is a huge amount of space. But the nucleus is so small, and this is a lot of energy, which is why nuclear energy is awesome. Very small amount of material yields a tremendous amount of energy to be able to turn turbines and make electricity, but also can be very, very, very dangerous. So who would ever mess with that? We are creating gamma radiation in Cape Girardeau every day at both hospitals, because when they do radiation therapy, this is the radiation that they use to treat the tumors. Why? Because they are trying to murder the tumors. They're trying to send so much radiation into those tumors that those cells die and can no longer reproduce. Okay? But the room where the tool is called a gamma knife. That's what it's called. The tool, the room where this is got 6 feet of concrete on each wall and the ceiling and floor, and the door is made of 3 feet thick lead. Like it, yeah, because this stuff is really crazy. Now, the other player in this that I want to talk about, directly related to wavelength, is a concept called frequency. And frequency is just the number of waves that pass per second. And it's measured in hertz, big H, little z. Hertz. H-E-R-T-Z, not S. Okay. So the general rule of thumb is this. The shorter the wavelength, the blank the frequency. What is it? Yes, the higher the frequency. Now, most of these waves travel by so fast that things are measured in megahertz, gigahertz, terahertz, like things really, really... Oh, your radio station, 96.5, is broadcasting at 96.5 megahertz. That's why it is 96.5, because it is broadcasting in a specific frequency. That's why... one last thing for that part. The higher the frequency, the greater energy the wave delivers. That's why the shorter waves here are dangerous and the longer waves aren't as dangerous. Now, you can make any of the other waves here dangerous if you wanted to, if you make them tall enough. Like, there's visible light that's dangerous. Those are called lasers. I use them to cut wood and engrave things at my house. Now, microwaves, obviously, you don't want to stick your face in there, okay? Because the amplitude is too high. All right. 2 quick questions. One was a trick question I gave you on the primer. Which of these does the sun produce? All of them. The sun produces all of these. The sun is sending radio waves and microwaves and infrared. Infrared is the reason why we're warmed by the sun when we stand out there. Okay? It makes visible light, otherwise we wouldn't be able to see. It makes ultraviolets while your skin gets burned. It makes X-rays and gamma too, but the ionosphere of the Earth protects us from these things. That's why if you ever go to space, you got to be careful and try to be protected from these other types of radiation. Okay, last little details. How fast does electromagnetic radiation travel? Anyone? You don't have to give me a number. Fast. Fast is right, yeah. The speed of light. And that's why it's called the speed of light. Answer. Speed of light. Speed of light. Which is 3.0 times 10 to the 8th meters per second, or 300 million meters per second, or 300,000 kilometers per second. Like, it's super, super fast. Okay? That's why you can get on your cell phone and talk to somebody in another city, and it's instantaneous. Your signal travels to the tower at the speed of light. Their signal travels to the tower at the speed of light. And you're able to communicate in what seems like no time at all, because that's how fast it gets there. Super, super fast. Now, what's faster, light or sound?
I didn't get that. Could you try again?
Yes. What's faster, light or sound?
Light travels at a considerably higher speed than sound. Light travels at a speed of approximately 299,792,458 meters per second in a vacuum, while sound travels at a speed of approximately 343 meters per second in air.
Yeah, okay.
This
Yeah.
answer...
Okay, smarty pants. She said approximately and then actually gave the decimal. 299,900. Okay, yes. 3.0 is rounded up. Okay, significant figures. But it travels, sound travels at 343 meters per second. So, and that's at standard temperature and pressure. So ballpark figures, light travels about 1 million times faster than sound does.